to degrade 99% of the drug, how many half-lives it will take? So 100 minus remaining is 0.78 after 7 half-lives. 789.3 something. So it will take 7 half-lives to degrade 99% of drug. Remember, this is the equation for first order kinetics. If it is in the log form, if it is in the natural log form, this is the equation. See, this is the equation if it is in the natural log form. There is another equation is also there, which is Ct is equal to C naught e to the power of minus Kt. Hi, today we are going to learn about pharmacokinetics in terms of GPAT. We try to see this in a short form. Pharmacokinetics, or you can say chemical kinetics, involves the study of rate of reactions. So we have order of reaction also defined as the rate of reaction, number of concentration terms on which the rate of reaction is dependent. If the rate of reaction is dependent on nothing, see here in this case this particular rate of reaction is not dependent on, it is dependent on nothing. I have written C to the power of 0, which is equal to 1. So it indicates the rate of reaction is not dependent on anything which falls under 0 order. Order itself is not there. 0 order kinetics. Okay. So if I remove the proportionality constant, see here in the next step we remove the proportionality constant to get a constant. We call it as 0 order rate constant, K naught. I denote it as K naught, that is your 0 order rate constant. Now take concentration terms on one side and time terms on different sides. So we have the concentration term here and the times here. Then we have differentiated things, so we want to integrate them. The things which are differentiated here is concentration and time. So integrate them, integrate the concentration from C naught to Ct. Now you can ask me, I have represented negative sign here, which indicates as the reaction is proceeded forward, the concentration of the reactants are being reduced. So if you integrate this particular thing, you will get, if you integrate this one, you will get this one. So Ct minus C naught is equal to K naught into T minus 0. So if you multiply this negative sign, you get C naught minus Ct, which by rearranging you get the equation for 0 order kinetics, that is 0 order constant K naught is equal to C naught minus Ct by T. Here C naught is initial concentration, Ct is concentration at time T, and T represents time. Now this is the equation. Now by using this equation you will get a questions like, here in this you will get a questions in GPAT from this equation like, they will be giving you the initial concentration, they will be giving you the time, they will giving you the value of the rate constant, and they will ask you to find out how much concentration is remaining at time T. So which can be done by this equation, or they won't give the rate constant, they will give initial concentration, they will give the time, they won't give the rate constant, they will give the half-life. Now by using a half-life, because they have given the initial concentration, by using this formula, using the half-life and initial concentration given values, you can find out the rate constant. In turn you have to submit this rate constant here to get the value of K naught, and you will get the value of Ct from the equation. So start with our equation. See here, this is the equation, this is the equation. In this equation what we have done here is T is taken as half-life. In the above equation, T is considered as half-life, which can be written like this. T is considered as half-life. Now send your T half here, it will be K naught into T half, and the Ct, concentration at time T. So in the half-life the initial concentration will be C naught only, it will be C naught. In half-life, at the half-life C naught will be C naught. We start from some initial concentration, but at concentration T, concentration at time T, at half-life is C naught by 2. So in one half-life it will be half of the initial concentration. That what is half-life means. So submit this here, you will get this equation. Solve this equation for T half. Once you solve the equation for T half, you will get this equation. So this is the half-life for the 0 order kinetics. What you can understand from here is, half-life is directly proportional to initial concentration. Means what? Means as the time progress, if the concentration is more degradation will be happening. If the concentration is less degradation will be happening in case of half-life of zero order kinetics. Remember, in case of first order, the concentration will not affect your degradation values, but in case of zero order in half-life, the concentration will affect your initial concentration will affect your half-life values, because T half, this particular T half, this T half is directly proportional to initial concentration. So remember this. Next we'll move on to first order kinetics. So in the first order kinetics, the rate of reaction is directly proportional to concentration of one reactant. So has written C to the power of 1. And I denoted negative sign here, which represents as the time progress the concentration of reactants will decrease. To indicate that, I have written the negative sign. Now remove the proportionality constant, you will get constant, that is rate constant of first order kinetics, K1. Now take all the concentration terms at one side and take your time terms of other side. Rearrange the above equation to get this equation. Now integrate the differentiated factor. The differentiated factor is dc by c, this one, and dt. If you integrate them, you will be end up getting natural log ct minus natural log c naught into t minus 0. So if you multiply this negative sign with this equation, you will get natural log c naught minus natural log ct and kt. Now log a minus log b is equal to log a by b. So by apply that formula, you will get natural log c naught by ct, which is equal to k1t. Now 2.303 log c naught by ct is equal to k1t, because natural log a is equal to 2.303 log a. So it is a conversion factor. Solve the above equation. This equation is been solved for k1. If you solve the above equation for k1, you will get 2.303 by t into log c naught by ct. This is the equation for first order kinetics. If it is in the log form, if it is in the natural log form, this is the equation. See, this is the equation if it is in the natural log form. There is another equation is also there, which is ct is equal to c naught e to the power of minus kt. kt. So this is exponent form. There are the three equations for first order kinetics. Remember this. One is natural log form equation, another is log form equation, another one is exponential form equation. Now we will move on to the half-life of this first order kinetics. So take our equation in the logarithm form. Take t as a t half here. This t is denoted as t half here. Okay, so at t half, what will happen to ct? I told at t half ct will be c naught by 2, half of the initial concentration. That what is half-life is. So substitute this equation here, you will get this equation. So c naught will get cancelled, remain is 1 by 2. So you will get this equation. So the value of log 2 will be 0.3010. Multiply this 2, you will get 0.693. So on the left hand side we have k1 and t half. So t half, solve the equation for t half. T half is equal to 0.693 by k. If you multiply 2.303 with 0.3010, you will get 0.693. So many people will ask me, sir, from where we are getting this value 0.693? This value is being derived from this equation after solving for t half. Remember. So what this equation is denoting us is t half is independent of initial concentration. So your t half is independent of initial concentration. So what do you mean by that? We will see by small exercise. So if you start with 100%, after 1 t half, see this is 1 t half, after 1 half-life, or you can say t half, 1 half-life, the concentration is reduced to 50%. Then now the initial concentration is 50%, after second t half it is reduced to 25%. So on, if we go till 7 half-lives, the concentration remaining is 0.78. Okay, 0.78 is the concentration remaining. Now why I am showing you this? Because there is a question in the GPAT. The question will ask you like this. The question is, what is the time taken for the, or how many half-lives does the first order kinetics will take to reach or to degrade 99% of the drug? Okay, to degrade 99% of the drug, how many half-lives it will take? So 100 minus remaining is 0.78 after 7 half-lives. 78125, this will be the value. So it will give almost 99.3 something. So it will take 7 half-lives to reach 99, to degrade, not reach, to degrade 99% of drug. Remember this carefully. Okay, it will take 7 half-lives to degrade the 99% of drug. What do you mean by that is, if the half-life value is 8 hours, so 7 half-life means it will take almost 56 hours to degrade the 99% of drug. So they may give the value. So the question will be like, how many half-lives, or you can ask how much time does it take for a first order kinetics reaction to degrade the drug from 100 to 99%. Okay, so to degrade 99% of the drug is been degraded. So they will give you the half-life value. The half-life is 8 hours or 10 hours. Accordingly you multiply and you can give the answer. So I hope you understand. Thank you.